1 is the deformation at 1 due to a unit load at 1, F2 1, and so on, right? So now, if you do this thing with this procedure over here, you will get the flexibility matrix after the damage, 2, which will prove to be minus CC in state 2 times the continuous transition matrix to the minus 1. The continuous time matrix, the second one, to the minus 1, that's not a square, that's just the second matrix, right? Times BC, the second one, right? So we have what? At this point, we have the ability, or we have been able to calculate the flexibility matrix of the structure at the location of the sensors from the vibration data. And we have the flexibility matrix before the damage, and we have the flexibility matrix after the damage. Now, when you read papers and so on this thing, sometimes it's not clear to people the following. The only reason, if I am going to use flexibility to try to locate the damage, right? This is what we would refer to as our feature. So the feature is the flexibility, is the fact that this matrix has changed. That's what we're going to use to locate the damage. Now, I don't need this flexibility matrix is a function simply of the stiffness, right? It has nothing to do with mass. It has nothing to do with damping. It's not a dynamical characteristics. It's just a static thing. Why do I go to vibration based? Well, the only reason is because it's kind of hard to go here and calculate the flexibility matrix in the field by applying the definition. I mean, I cannot really come here and say, let me apply a unit load or a load of any nature and measure how much the points moved. Then let me come here to this level and apply a static load and see how much the levels move. If I could do that, then I would do that, because the flexibility computed that way is going to be more accurate, right? I don't have to worry about the noise and the vibration measurements and all of that, but I can't. So I am relying on vibration data to obtain a property which is actually a static property of the structure, okay? So we now have the flexibility before and the flexibility after. Okay? Now, let's designate these flexibilities as F in the reference state and F in the damage state. I've been calling them 1 or 2, but I think reference and damage from now on will be clearer from the discussion, right? Flexibility in the reference state, flexibility in the damage state. For this case, these matrices are 4 by 4. In general, they are number of measurements by number of measurements, assuming that we had one input that was collocated, right? Or size of the union of the experimental coordinates, provided that there is at least one collocation. Now, this is the logic of the DLV approach. It goes like this. The flexibility in the reference state multiplied by loads would be the displacements of the reference state, right? Now, the flexibility in the damage state, if I multiply it by some loads, will be the displacements in the damage state, correct? And this load is the same. Now, this is clear, right? Equation 1, equation 2, that just means I'm taking a load, which I didn't say what it is, some vector L, which in this example would be 4 by 1, right? Because our flexibilities are 4 by 4. And if I took an arbitrary vector L and I multiply it times FR, I will get 4 displacements. And if I multiply it by the FD, I would get 4 displacements. Now what I do is I say, let me subtract these two equations. So I have that the flexibility in the damaged state minus the flexibility in the reference state multiplied by L, which is common to both, is equal to the deformations in the damaged state minus the deformations in the reference state, right? That's very simple, very obvious. Now, this means that this here, which is the change in the flexibility, multiplied times whatever load we decided to apply, is equal to the change in the observed displacements, right? Okay, so far so good. Now comes the idea. At this point, you say, let's examine the rank of delta F. Delta F, right, it's a matrix, in our case, that is 4 by 4. I'm using numbers to refer to this one. But if we take a singular value decomposition of delta F, we will get something like this. Right? Where these are the left side singular vectors, these are the singular values, which will be 4, right? And this is the right side singular vectors, which times L is equal to delta D. Now, if delta F is full rank, then this approach does not apply, meaning we can no longer find where is the damage if delta F is full rank. And in fact, it makes sense, because if delta F is full rank, the damage is everywhere. Well, actually I shouldn't say that, because I don't have sensors everywhere. But the point is that delta F will have a rank in most applications of interest, and I will clarify further in this case and so on, that will not be full. Therefore, let's say that in this case the rank of delta F was 3. So if the rank of delta F is 3, that means that this singular value is 0. Okay? I mean, it could be 2, it could be 1. Now, could it be 0? Yeah, it could be 0. But if the rank of delta F is 0, that means that delta F itself was 0. That means there was no damage, because that means that the flexibility before and after were the same matrix. So the rank of delta F is either 1, 2, 3, or 4 in this particular case, right? Now, let's say that the rank of delta F was 3. That means that there is 1, 0 singular value. What that means then is that there is a vector L. In fact, in this case, the last column of V, in our case, has 1 column, 2 columns, 3 columns, and then this column of the vector B is the null space, right? And we call it Z. So that vector, the last vector on the matrix V, is such that if I take that and I multiply it times delta F, I get 0, right? Therefore, delta F multiplied times Z is equal to 0. Or if L is taken to be Z, then there is no change. Okay? Notice then that what I'm saying is the change in the displacements between the damaged structure and the undamaged structure for an arbitrary loading is something. but there is a certain loading. If there is a zero singular value, that load distribution produces no change on the displacements. Even though the structure is damaged, for that load distribution you see nothing. Okay? So, then the question is, well, what is the meaning of that you see nothing? Well, you can check the derivations in the paper in detail, but what it means is that if I find a vector L for which this is 0, which is in the null space of delta F, right? Then the right side is 0. Then the question you have to ask yourself is, how come the structure is deforming exactly the same at the sensors due to that load? And the answer is because there are no stresses acting at the damage location. So for example, and that's how we find the damage. So for example, if we had this 4, 3, 2, 1, no, 1, 2, 3, 4, 5, I should say, wait, one more. Now let's say, for example, that the damage was here. So let's say that the damage was on the first floor. Now, there was a damage on the first floor. The vector L is going to have values which are to be interpreted as being loads here. It has 4 numbers, right? Now, I don't know what it is, it depends on the numbers, but let's say it proved to be 10, 6, 2, 18, for example. That vector, which I just drew there, could be the vector L from the null space if the damage was here. Because what that means, since this is a shear building, is that the shear stress here in this is 10, then is 16, then is 18, and then is 0. So it's 10, is 16, I guess I missed one jump, is 16, is 18, and then is 0, right? So, for this loading, there is no shear on level 1. And if there is no shear on level 1, in a shear building, there is no distortion on level 1, therefore the stiffness of level 1 is irrelevant. And that's why a change in stiffness of level 1 cannot be seen on that delta F. Alright? Now, if in reality the damage was only on level 1, what we would find is that the delta F would only be rank 1 in a problem like this. Okay? The delta F would be rank 1. So the singular values of delta F would actually be a number and then 0, 0, 0. Okay? If there was a single damage. What that means is that of the matrix V, there would be something here. The next 3 columns are in the null space. So this is in the null space, this is in the null space, and this is in the null space. And these are all damage locating vectors. Because the stress here will be 0, not only for the last one, but also for the one before the last and for 2 before the last. Okay? That you would say, but why do I need more than 1? I mean, I already got it with 1. And that may be true sometimes. But the important thing to keep in mind is that what the damage locating vector approach states is not, and this is important to be understood, the method doesn't say that where there is a zero stress, the damage is there. What it says is that where there is some stress, there is no damage. So you could have, for example, a situation like this. Let me see. What did I have? 3, 4 loads. We could have another load here, right? For example, I could have that vector. That vector also could be in the null space if the damage was here, because that gives me 10, and then gives us 12, and then gives us 0 all the way down. So it does satisfy that there is no stress in the damage location, but there is no stress also here, which is not damage, right? So the approach doesn't say there's anything wrong with that. It just simply says, when you see a non-zero stress, you can discard that. The damage is not there. So in this particular case, depending on the problem, it may be that any one of these vectors is already the answer. But it may be that it is actually the superposition of this and this and this that eventually leaves you no choice but that the damage was here. Okay? On level number 1. In its most basic form, the damage locating vector approach, static, is as I've just explained. This is the DLV scheme. Now, in its most basic form. The problems that arise in practice come from a number of sources. The first one is that the identification is never perfect. And so you have an F in the reference state and you have an F in the damage state, but they are distorted, right? They're not exactly correct. So when you calculate the change in F, what you get is not the exact change in F, but something distorted, right? So when you do the singular value decomposition of the change in F, you may not, actually, you will never get exactly zeros. So you may get something like this, 10, 2, 0.1, 0.05, let's say, just making things up. Now, in this case, you would say, well, okay, it looks pretty small compared to 10, so this is probably a pretty good estimate of a damage locating vector. But what about this one? Is that also small enough? I'm not so sure, and so on. So one of the issues that arises in applying this approach is how to decide on the singular values which ones you consider to be sufficiently small to treat the vectors as damage locating vectors. Okay? In the paper, there is a guidance as to how we do that computation. And I will post the paper for you guys on Blackboard for you to see. The other issue, not issue, but the other thing that arises is how should one aggregate the results for various vectors. Let's say again, if the data is perfect, none of these issues matter. The problem is when the data is not perfect. So you have a flexibility matrix change, and the flexibility matrix change gives you singular values S1, S2, S3, and let's say these last three are small. okay? So you got 3 significant and 3 small, and what I say by this 3 small, I mean following the guidelines in the paper and whatever it is, you think that maybe these 3 things are damage locating vectors. Now, when you take the structure, each one of these, vector, DLB vector 3 gives something, DLB vector 2 gives something, and DLB vector 1 gives something. So you get, something like this, whatever at the sensors, another one here, and another one here. And so on, right? So these are the loadings that you got from these 3 things. Now, let's say that the value that you got from DLV, I'm sorry, this is, let's say this is 3, 2, and 1 or something in this order. So let's say that this is really good. So, we get a stress here, let's say here in this level of point, let's say everything is normalized to maximum stress of 1. Normalized to max equal to 1, so it makes some sense in the discussion. So I do this loading, and then I make the maximum stress equal to 1, and this is 0.1. Then I come here, and I do the same thing for the second vector, and this one is 0.12. But let's say that when I did number 1 was really poor. And so it turns out that over here, it turned out to be 0.22. Now, if I have previously stated that my threshold for eliminating something was 0.2, then I'm going to make an error because one of the vectors didn't confirm it. Okay? If I establish a threshold of 0.20 to say anything above 0.20 is not damaged, then I would make an error because even though this is correct and this is correct, this one is a little bit over. So the way that we apply the DLB approach when there is more than one vector is not by elimination, but is by some sort of averaging. That is, we simply make the paper describes a reasonable average of the stresses that we get for all the various loads, and that's how we eventually get a single pattern from which you decide. Okay?